It's clear. All right. Good morning, everyone. Thanks for being here. We are very happy today to have Mustafa Sadeghi in the MIAI Deeptails seminar. So Mustafa did his PhD in Sharif University in Iran, and he was a visiting scholar in KTH and here in Grenoble with Christian Jutin. Well, then he came to INRIA for a couple of years of an excellent postdoc, I would say. And then he was recruited at INRIA Nancy, where he has been doing research on audiovisual speech enhancement for these past 4 years. And today he's going to talk about generative models for as speech priors. So please join me in welcoming Mustafa, and we are looking forward to your talk.
Thank you, Shai, for the introduction, and good morning, everyone. So today I'm going to talk about how generative models can be used as speech priors for speech enhancement. So the presentation is a structure like in 3 main parts. So first, I will give a brief introduction to the speech enhancement problem and different categories of algorithms that exist. Then I will talk about variational autoencoder to be used as a speech prior, and then diffusion models. So speech enhancement is a fundamental problem in signal processing machine learning, where the goal is to estimate clean speech from a noise observation. And it has many practical applications, like in daily life conversations, in Zoom meetings, even in the crowded areas for listening comfort, but also for hearing assistive devices. And recently, due to this rise of technology for visual assistants, it's also very important for interacting with visual assistants and social robots. And many algorithms have been proposed for this problem. And there are, of course, different categorizations of methods. But for the sake of this presentation, I divided different algorithms into 2 main categories. The first one, which is the dominant category, is supervised methods, where they simply try to estimate in the speech given the noise observation. So we could say that they try to model the posterior distribution with some parametric models like deep neural network. And then given a paired data set of noise and clean data, they learn this set of parameters. So within this supervised method, we can consider 2 subcategories. The first category is regression-based, where they try to directly map noisy speech to an estimate or to predict the time frequency mask. But there is another recent category where they use generative-based approaches. So basically, they incorporate the speech generative models, especially diffusion models, used to generate clean speech, but conditional noisy speech. So they try to train a generative model to generate clean speech, and they use some guiding information given by the noisy speech signals, right? Or these generative models could be used as a post-processing step on top of these regression-based models. So they work really well on scene data or match condition, meaning that the test conditions are similar to the training conditions, but as soon as we see a new environment, new test conditions, their performance drop. So in addition to this group, we have unsupervised methods, where the goal is to do speech enhancement without relying on paired data, okay? So we assume that we have clean speech data and noisy speech data, but they are not paired. So within this category, we can define 2 main subcategories. So the first ones are generative priors, where instead of directly modeling the posterior, we decompose it using base tree into 2 terms. So the first term is likelihood, which is given by the observation model that we define. And the second term is simply the prior distribution of clean speech signals. And the idea is to do speech enhancement in 2 steps. So we have a pre-training step where we train the prior distribution. And then at inference, we do the speech enhancement by combining this prior with the observation model and doing posterior sampling. So there's another category, which is on-pair training. So we have different approaches like mixture invariant training, domain adaptation techniques. That again, they try to adapt domains of clean speech and noisy speech signals. So in this category, we have better generalization than supervised methods because we do not train on paired data. But they lag behind supervised methods on scene data, right? So the focus of this presentation is generative-based methods. So the general approach of unsupervised generative-based speech enhancement is to estimate clean speech by directly sampling from the posterior, right? Where, as I said, we pre-train prior distribution on clean speech data only, and then we consider noise model like non-negative matrix factorization, where we assume this likelihood model, right? So basically, the variance of this Gaussian distribution is structured with NMF, with 2 low-rank matrices, which is a good model for stationary types of noise. And how we solve this problem, or speech enhancement problem, we use iterative expectation maximization, where we need to estimate the parameters, which are the NMF matrices, using this maximization problem. So we see that we have a posterior term of clean speech given noisy speech. So in the E step expectation, we draw clean estimates using posterior sampling, given the current estimates of the noise parameters. And in the maximization step, we maximize the likelihood using the obtained clean speech estimates to update the parameters. And we do these iterations several times until we get some convergence. And finally, we can get the posterior samplers as clean speech estimates. All right, so now I'm going to talk about how we can use variational autoencoder to model the prior distribution of clean speech in the pre-training phase. So for that, we usually work in the short time Fourier transform domain, where we can define this sequence of STFT timeframes, where each time vector is an array of complex valued numbers. And the generative speech prior that we consider in the MIAI framework is like this. So we have the likelihood for the generative model, where we assume that each speech time frame is generated using some latent variables. And the distribution is assumed to be zero mean complex valued Gaussian, where the variance is structured as a neural network, taking the latent variable as input. We also assume a prior distribution, which is usually a standard normal distribution. So as I said, the sequence of Z vectors are real valued latent variables associated to each speech time frame. And this nonlinear function is parameterized by a decoder or generative neural network. So in this case, we can generate or model clean speech given the latent variable. Okay. So the goal is to learn this set of parameters, theta, using some clean set of speech signals. So for the training data, we consider STFT arrays of clean speech signals. And then the training objective would be to maximize the marginal likelihood, as you can see in the first equation. But this equation is intractable to compute due to the intractable integral. So the idea of MIAI is to use variational inference and maximize the variational lower bound instead, which you can see here. So in this lower bound, we have defined an auxiliary posterior distribution, which approximates the true posterior distributions of latent variable given clean speech signals, right? So this is similar to the generative model, a parametric distribution with parameters defined as psi. So we need to estimate these parameters to be able to learn the generative parameters as well. So after some simplifications, we can get this final training objective where we jointly optimize the parameters of the decoder or generative model and those of the encoder or the approximate posterior distributions that we just defined. So we have this encoder-decoder architecture where the encoder approximates the posterior of latent variable given the clean speech data. And the posterior distribution acts as a generative model to generate clean speech given the latent variables. So we can learn these parameters using reparameterization trick and gradient optimization. So in this way, we can train the prior distribution on clean speech, where we can sample from it to generate clean speech, right? And the process of generating new speech signals is to first sample a Gaussian latent variable using this standard Gaussian distribution. And then you pass it to the decoder to reconstruct the speech in the output of the decoder. So here you see an example of speech generated using VAE, where by looking at the spectrogram, you can see that the model has successfully captured some phoneme structures for the speech signal. So I'm going to, so another point about VAE is that the VAE models only the spectrogram. So it means that we need to estimate the phase of the SCFD to be able to reconstruct the time domain speech signals. So for that, there are several algorithms to be used. So I'm going to play the speech signals generated like this. So we see some phoneme structures, silences, etc., but the speech is not really intelligible, right? So now that we have trained the prior distribution, the next step is to do speech enhancement, right? And for that, we can still represent model for clean speech modeling. And for noise model, we can assume a non-negative matrix factorization, where we assume a zero mean complex value distribution for each SCFD time frame of noise, where the variance is structured with two low-rank matrices to be estimated. So using this, we can compute the likelihood in closed form, and it remains to estimate these WH matrices. So for that, the dominant approach is to follow a variational EM methodology, where we need to approximate this posterior distribution of latent variable given the noisy speech, right? Which is interactable to compute. But the idea of variational EM is to use the pre-trained encoder, which has been trained on clean data, and fine-tune it on the noisy speech to approximate this interactable posterior distribution, right? So you see a very similar objective function as in the VA training, where we have replaced clean speech with noisy speech. So we keep we fine-tune these psi parameters, right? The encoder parameters. Then once we fine-tune it, we are able to sample from it because it's Gaussian distribution and very easy to sample from, right? And then we can replace these samples, use these samples to approximate the expectation in the above equation. So this was the E step, and for the M step, we need to update the parameters by maximizing the objective function. So there are many algorithms for that. All right, so once we do these EM iterations and we get some convergence, we can estimate the clean speech using posterior mean, where after some simplifications, we can see that it leads to a winner-like filtering operation, right? So we use the approximate posterior distributions of latent variables. We take some samples and then we compute this winner filtering operation using the optimal parameters that we have obtained. All right. But this approach, the variational approach, is computationally expensive because we need to fine-tune the parameters of the encoder at every step. So it means that if we have a complicated encoder, then we have many parameters to optimize, and it will slow down the inference process, right? So that motivated us to introduce more efficient inference methods, which are based on posterior samplings. So the idea is that instead of approximating the whole distribution, the posterior distribution, we directly sample from it, right? And we propose fast and efficient samplers based on zero or first order optimization. So here you see this pseudo algorithm for that, where the overall process remains the same, but we modify the E step. We replace it with some sampling operations to generate latent variables to be used in the M step to update the parameters. So in the following, I'm going to discuss some sampling methods that we have developed for speech enhancement. So the first one is the famous metropolis testing algorithms, that is an iterative Markov chain Monte Carlo method, to be used in situations where the posterior distributions is known up to a normalization factor, right? So we adapt this MH algorithm to the speech enhancement problem. So for that, we need to sample from this posterior at the E step. So we follow these iterations. We start from some initial latent variables. Then we generate some next candidate samples using these proposal distributions. So we basically starting from the initial latent vectors, we move in some random directions. We generate some candidate samples. And then we have a refining step where we check whether we need to accept these samples or keep the current ones, right? So this acceptance probability is basically obtained using relative posteriors. So relative posteriors of the newly obtained samples with respect to the previous ones. So the main point here is that we compute these probabilities in parallel for every latent vectors because it's more efficient than doing it frame by frame, right? So it means that we avoid updating these probabilities for each vector and then go to the next vector and update these terms. Instead, we do parallel sampling, which is much more efficient. So the second algorithm is Langevin dynamics, which is again a famous posterior sampling algorithms relying on the score function. So for that, we need to compute this term, which is score, and you can compute it in efficiently because you don't need the normalization factor of the distribution, right? So as you can see, you can compute the score function as the sum of these two terms, one term that comes from the likelihood, and the second term is the prior of the latent variables, and you can compute this gradient efficiently. So what we develop is to consider multiple samples per time frame because the posterior space is mostly multimodal. So to better explore this posterior space and cover most of these modes, we consider multiple samples per time frame. So it means that in the end, we will have multiple estimates for clean speech that we can aggregate to arrive at better and more robust estimates. And to generate these multiple samples, we follow this proposal distribution, which is a random walk again. And then we generate next samples using these proposal distributions, where compared to the metropolis testing, we have an additional guiding term, the score function, that guides this movement to move towards like higher posterior regions, right? because the score function is related to the score to the posterior distribution. So we can equivalently write this proposal sampling using this last expression, where you see that we are injecting some Gaussian noise. So here, as I said, the posterior space is multimodal. So that's why you can serve multiple samples for each time frame, because we are more likely to cover those modes. And then to move towards those modes, we can serve gradient ascent steps. And in this approach, we have noise injection to better explore this posterior space, right? And to skip this local maxima. And compared to MH, we do not have any acceptance rejection mechanism. So lastly, we use Metropolis adjusted Langevin algorithm, which basically combines these LD steps with MH. So it adds some acceptance rejection mechanism to the LD approach. So generating the next samples is similar to the previous approach, but we add an acceptance step using these probabilities, okay? So compared to the Metropolis testing, this MIAI algorithm tends towards higher probability regions because of this direction given by the score function, right? So now I'm going to present some quick results. So we can say 2 data sets to simulate matched and mismatched condition. So we can see just one sampling iteration for the LDEM, while for MHEM and MIAI-EM, we consider 10 sampling iterations at each ES step. And in addition, we consider 10 parallel samples for the LDEM method. So as the baselines, we consider a pre-trained recurrent variational autoencoder method, as well as state-of-the-art diffusion-based supervised methods, right? So for the performance metrics, we consider standard metrics like SISDR, PESC, which is about perceptual quality of estimated speech, STOI, which measures the intelligibility, and RTF, which is a measure of runtime efficiency. So it's basically tells us how much time an algorithm takes to process 1 second of speech signal, right? So here we see the results for the matched condition, meaning that the test condition is similar to the training condition. So here we show the input metrics, then the result of VEM, variational EM, and then the 3 posterior sampling based methods, and finally this state-of-the-art algorithm. So first we see that compared to the VEM, we have slightly improved the performance with these sampling based methods. Another significant point here is that, as expected, the performance of the supervised method is much better than the unsupervised methods because we are in a matched condition. So that's why we see this significant performance gap between unsupervised and supervised. But when we move to the mismatch condition, meaning that the test condition differs from the training condition, we see a significant drop in the performance of SGMSE, the supervised approach, while the proposed sampling-based methods are fairly robust. Another point is about the VEM. We also see a performance drop for VEM because, as you remember, this approach is based on fine-tuning the encoder. It means that if the encoder is trained on another data set than the test set, then similar to the supervised approach, we have this performance drop. So in this case, our proposed sampling-based methods work much better than the VEM approach. And finally, here we compare the runtime efficiency of different approaches. So the numbers that you see on top of the bars denote the speed up factor compared to the baseline VEM. So we see that this LDEM is significantly faster than VEM, like 60 times faster. And that's because, well, in the encoder fine-tuning, there are many parameters and it takes many times, not computationally efficient, while for LDM, we are optimizing with respect to the latent vectors, which are of much lower dimensionality than the encoder parameters. All right. So now I'm going to move to the diffusion models, right? So the diffusion models are a recent state-of-the-art class of generative models that have been extensively used in different areas like image generation, video generation, and audio generation. So I'm going to define, to introduce these models in the context of speech modeling. So diffusion models involve two processes, the forward or the noisy process, where the task is to gradually add Gaussian noise to the clean speech signals. So we start with the SDFT of clean data, then we iteratively add some Gaussian noise, where we can describe this forward process using the stochastic differential equation that you see in the first equation, right? So that SDE has an associated perturbation kernel that you can see there in the boxed formula, which simply scales the clean speech data at each time step and add some Gaussian noise with increasing variance, right? So in the end, we'll have completely Gaussian sample. But the generative process is done in the reverse or the denoising process, where the task is to start from some Gaussian noise and iteratively remove the added Gaussian noise to arrive at clean speech estimate. So it can be shown that the forward ST has the associated reverse ST that you can see here. And in the highlighted equation, you see the score function, which is interactive to compute. So diffusion models try to estimate this score function using some neural network modeling, where many objective functions have been defined to learn the parameters of this score model, right? So you can see the most popular one, denoising score matching objective function here. So once we learn this score function, we are able to run the reverse or denoising process to basically sample from the prior distribution. And we have different kinds of solvers for the reverse SD. So here you see a summary of diffusion models. So in the top, we see that we are trying to go from the data distribution to the Gaussian distribution within the forward process or the noisy process. While in the reverse process, we start from some Gaussian distribution and we iteratively run this reverse process with the help of directions provided by this score model, right? So these score models act as a denoising model to obtain the next samples until we get to a clean speech at the end of the reverse process. So this is the architecture of the score model that we have used. So the main point here is that this is a multi-resolution unit that has been used a lot in the image domain. So this architecture has been adapted to speech modeling, where we give as input concatenation of real and imaginary parts of SDFT. So it means that in contrast to VAE, we model the direct complex value SDFT arrays, right? So here, the product sampling process is similar to VAE. So we start with some Gaussian noise. Then we run the reverse process starting with S, right? So here you see a sample speech spectrogram generated using diffusion models. And compared to the VAE one, we see that it's like it has better quality. And if we listen to the speech, so the quality is much better than the VAE one, but still, I mean, the speech is not intelligible because, as expected in the diffusion models, we have no mechanism to incorporate that condition. So now that the prior has been trained, the next step is to develop an speech enhancement methodology, right? So the approach is based on EM, again, similar to VAE, where in the E step, instead of running the prior sampling, we replace the prior term with the posterior distribution. So you see the score function on the posterior distribution, which can be decomposed into two terms. So the term in blue is simply the score function that has been pre-trained on clean speech data. But we have this additional first term, which comes from the likelihood, okay? So compared to the prior sampling, this new term basically tries to incorporate the noisy speech information to, to guide this speech generation towards generating speech signal that is consistent with measurements, right? But the problem here is that this term, this likelihood term, is intractable because it depends on time. And there are many approaches to approximate this term. So we have used one very simple approach that ends up with this closed form expression, right? And then with this term, we have all the information needed for the ES step, right? Yes.
So here the time is the diffusion time, right? Yes.
Yes, exactly.
It's not
Not to be confused with this.
It's not the temporal.
Yeah. Thank you for that. Yes, exactly. So this is the diffusion steps. And ST basically is the whole array of STFT here, right? So with this approximation, we can run the reverse process to get an estimate of clean speech. And in the M step, we update the noise parameters with that estimated speech, which we can use like same NMF algorithms as in VAE. So here I try to schematically describe what's happening in the diffusion-based EM steps. So we have a data manifold, which is trained by the diffusion model on clean speech data. So the orange space. We have another set which comes from the noise observation. So it's a feasible set that tells us that basically makes some constraint on the clean speech signals, right? So in the diffusion process, we start with some Gaussian noise here. Then if we only follow the directions given by the score network, then we will have prior sampling. It means that we'll end up at some point on the data manifold, which is not necessarily consistent with observation. But if we modify these directions using the likelihood term, then hopefully we'll move towards the intersection of the two sets, right? So basically, we follow the E step by starting from this Gaussian noise, modifying the trajectories using the likelihood term, and then getting a speech estimate in the end. Then we should know that this feasible set is parametric. So the parameters are the NMF parameters, so we need to update them, right? So that's why in the M step, we take this speech estimate that we get to update the NMF parameters, phi. And we repeat the EM step several times. So in practice, like 5 EM iterations are sufficient. Okay. So now I'm going to quickly discuss how we can do audiovisual speech enhancement with diffusion models in an unsupervised way, right? So audiovisual speech enhancement is motivated by the fact that speech communication is multimodal. When you speak, you have lip movements, which are correlated with what you are saying, right? Especially if you are in noisy environment, looking at the lip movements could help to better understand the speech. So that's why in audiovisual speech enhancement, this complementary information provided by video is incorporated to improve the quality of speech enhancement. So how we can incorporate this information into the diffusion framework that we just discussed? All we need to do is to replace the score model with an audiovisual version. It means that now we are also taking visual features coming from the LIPS video. So how this LIPS video could help improving the performance in this unsupervised case? Well, if we do not have this video information, if we run the prior sampling, we will generate a random speech signal. But if we incorporate this video will act as some guiding information for the speech generation. So if the fusion is done properly, then at the end of prior sampling, we hope to see a speech signal that is somehow correlated or consistent with LIPS video. In this way, the prior model itself basically helps going in direction that is not far from the feasible set, right? So for the audiovisual case, we are modifying these prior sampling iterations towards the feasible set.
Okay, be sure that the video introduces noise.
I mean, if the video is clean, I mean, frontal, everything, then we hope to incorporate this information for the speech generation. But if, of course, it's noisy, then we need to have a mechanism to, to either correct it or ignore it, right? But for now, we have tested this with just frontal videos, clean video. But of course, I mean, it needs to be adjusted to real world conditions. Right. So now I present some results. So we have three data sets for simulating mismatch conditions and audiovisual setting. So here, in addition to the objective measures, we have considered some pseudo-subjective measures provided by some deep neural network, estimating mean opinion scores. For the baselines, in addition to the audio-only methods, we consider recent audiovisual methods, flow AVSE, which is based on flow matching generative modeling, right? So the model architecture is a multi-resolution unit that I showed, which is a similar architecture as in SGMSC speech enhancement. So here we see the results of audio-only speech enhancement. So on top we have the match condition, and in the bottom we have the mismatch condition. So in the match condition, again, we see this gap between unsupervised and supervised methods. And we see that in terms of these metrics, we have similar performance as with VAE method. In the mismatch condition, we see that, again, for the supervised, we have problem, this generalization problem, performance drop. But the unsupervised methods work more robustly. If you look at these pseudo-subjective metrics, we see that compared to VAE, diffusion models work better. It was something that we also listened by listening to the examples. We noticed that diffusion models reconstruct speech of higher quality than VAE. And finally, I present the results of audiovisual speech enhancement. On top, we see the match condition, and in the bottom, we have the mismatch condition. So the first point is that by adding the visual modality to the diffusion model, we have a performance improvement, like 2 dB in the SDR and similar improvements in terms of PESC and STOI. Again, we see this gap where this supervised method outperforms unsupervised methods in the match condition. But again, we see this robust behavior of unsupervised methods in the mismatch condition, right? All right. So as some conclusions, we reviewed data deriving speech priors. to be used for speech enhancement. And we noticed that, I mean, this approach could be really versatile for several reasons. First is that they have better potential for generalization than supervised methods. They have better interpretations compared to supervised methods because, you know, we have this combination of prior and noise model, then we can better tune the contributions and to see what's happening in the output. So we can modify the speech model, the observation model, which is not really clearly seen in the supervised method. Then another advantage is that with a single pre-trained model, we can do many inverse problems. All we need to do is just to replace the observation model, right? So keep the pre-trained speech model the same. And for each task, we update the observation model for dereverberation, in-painting, etc. But we also noticed that unsupervised method speed falls short compared to the supervised models in match conditions. And they are computationally more expensive because they are iterative-based methods. So for that, we propose some sampling-based methods to decrease this computational gap. And we noticed that they could be really efficient for speech enhancement with like faster runtime. We proposed the first application of diffusion models for unsupervised speech enhancement. It was mainly a proof of concept, and we showed that diffusion models are really efficient compared to VAEs for speech enhancement, but of course they are computationally more expensive. So of course, as future works, we need to work on how to improve the computational efficiency of diffusion models to bridge the gap between unsupervised and supervised approaches. Right. So here I put some links to audio examples if you want to listen. And thanks a lot for your attention. So I would be happy to answer your questions.
Time to ask difficult questions to Mustafa when I stop the recording.